And welcome to the second lecture on this lecture series on electronic communication systems. In the previous lecture, we studied about the basic building blocks of electronic communication system, and then we started our discussion about amplitude modulation. So, in this lecture, we will continue that discussion on the amplitude modulated waves. But before going into details, let us try to quickly revise what we studied in the last lecture. So, we saw that the basic building block of modern electronic communication system has essentially three parts. One is a transmitter. This transmitter itself is a system. It is not a single entity, it is a system, and from which a channel is connected. And finally, the third block is the receiver. In channel, there may be some noise that is associated with the signal. So, these three are essentially the building blocks in communication system. Before transmitter, there is the source of information, and after the receiver there is a person, or you can say the receiver of information. We also saw that transmitter contains an inbuilt section that is basically a transducer. The role of transducer is to produce electrical signal from the message signal. So, the message signal may be a voice or a video or photograph, or it may be data file. So, the first job is to convert this information signal into electrical signal. Then we saw that since the frequency, we were discussing about the audio signals, how to transmit audio signal, and we saw that the frequency of audio signal is so small that it cannot be transmitted as such. The antenna, the dimension of antenna that will be needed to transmit the voice signal as such converted into electrical signals, and as such if we want to transmit it, the dimension of antenna will be several kilometers. Whereas if we increase the frequency somehow, the requirement of dimension of antenna decreases. The dimension of antenna is inversely proportional to the frequency. Second requirement was that the energy, the intensity of voice signal as such is very low. So, that is the second reason why we want to use high frequency waves. Intensity of any wave is proportional to the frequency of that wave. And third requirement was that if we want to transmit more than one voice signal at a time, and if we are transmitting these voice signals as such, of course converted into electrical signals, then there will be huge interference because of the matching frequency, and it will be very difficult to distinguish, virtually impossible to distinguish between the sources which have produced these voice signals. Then we derived the equation of amplitude modulated wave. So, if I write the information signal as EM, that is our message signal, you can also say that is our message signal, and if it was given by the electric field was given by EM naught sine of omega mt. Omega m is the angular frequency of message signal. This is the amplitude part, and if the carrier was given by the electric field of carrier was given by E c naught sine of omega c t. Then we have seen that amplitude modulated wave will look like E c naught plus E m sine of omega c t. The carrier frequency does not change. This is amplitude modulated. So, let me write this is amplitude modulated and this was carrier wave. This is carrier wave here, this is amplitude modulated wave, and this of course was our message. And we also saw that the resultant amplitude modulated wave has 3 frequencies. One is omega c, that was our original carrier frequency. And a slightly increased frequency by an amount of modulating frequency and a slightly reduced frequency by the same amount of omega m. So, this was lower sideband and this was upper sideband. We were then discussing about the pictorial representation of amplitude modulated waves, and in defining this amplitude modulated wave we also had defined a quantity that is the modulation index, and we have given represented that by mu, where mu was given as the amplitude of modulating wave divided by amplitude of carrier wave, or in terms of our representation it was equal to E m naught divided by E c naught, which is equal to amplitude of modulating wave. Modulating means our original message wave divided by amplitude of carrier wave. This is very important, and this mu is known as amplitude modulation index. And we were discussing what is the role that amplitude modulation index plays in amplitude modulated wave. So, now let us focus on mu. So, we know that mu is equal to E m naught divided by E c naught. This is the amplitude of modulating wave divided by amplitude of the carrier wave. Now, what we can do is we can write this whole thing equal to 2 times E m naught divided by 2 times E c naught, and we can also add and subtract the same quantity. Let us say I am adding E c naught and I am subtracting E c naught from the numerator, and let us say that I am adding E m naught and subtracting E m naught from the denominator. Now, if I slightly rearrange the terms, what I will get is this thing is equal to E c naught plus E m naught minus E c naught minus E m naught divided by E c naught plus E m naught plus E c naught minus E m naught. What this tells me, if I focus on the very first quantity in the numerator, first quantity is maximum of amplitude modulated electric field. If you remember, electric field of amplitude modulated wave was given by EC naught plus EM sine of omega m t, let me erase it, omega m t, this was the amplitude, and this thing was multiplied by sine of omega m, omega c, this is omega c, carrier frequency does not change. So, the wave was given by this. So, I can see that maximum electric field, maximum of amplitude modulated electric field is given by E C naught plus E m naught. This was E m naught here. And we also know that minimum of amplitude modulated electric field is equal to E C naught minus E m naught. So, maxima happens when sine of omega m t is equal to plus 1, and the amplitude of amplitude modulated wave becomes minimum when sine of omega m t is equal to minus 1. So, using this we can write the amplitude modulation index mu being equal to maximum of amplitude modulated wave minus E minimum of amplitude modulated wave divided by E max amplitude modulated wave plus E min of amplitude modulated wave. So, this is another way of defining the amplitude modulation index. Now, let us see what happens when mu is equal to 1. In the previous lecture we have already studied what happens when mu is smaller than 1, and the specific case that we considered was when mu was equal to half. That means the amplitude of modulating wave is half as compared to the amplitude of carrier wave. So, let us try to revise that and then we will proceed. So, if I represent the electric field on the y axis, here is the electric field and here is the time axis, that is the horizontal axis, and this is equal to 1, this is equal to minus 1. So, I am considering plus 1 and minus 1 being the maximum and minimum of amplitude of the carrier wave, and if mu is equal to 1 divided by 2, I have to consider half as the amplitude of the modulating wave. So, modulating wave will have a maximum here and a minimum here. So, this will be basically 1.5 and this will be 0.5. So, my amplitude modulating wave will behave like, let me draw it, will vary like this. So, this is 1.5. So, this will have a maximum value here and a minimum somewhere on the lower side. Similarly, from the other side, the amplitude modulating wave will vary like this and like this, and the amplitude modulated wave now behaves like this. So, it will vary inside this envelope that is generated by the modulating wave. So, the blue colored curve is now amplitude modulated wave. This blue colored curve is amplitude modulated wave. So, the red curve that appears in this figure is just to represent the envelope of amplitude modulated wave. The amplitude modulated wave as such will look like the blue curve in this figure. Now let us see what happens when mu is larger than 1, and let us say it is equal to 3 divided by 2. And let us draw this figure again. So this is my vertical axis, that is my horizontal axis, here is time and here is the electric field. Now once again I am going to consider the electric field of carrier, the amplitude of carrier wave being equal to 1. Let me represent this by blue curve. So amplitude of carrier wave is 1, and of course in the negative side it goes to -1, and amplitude of modulating wave or our signal wave is 1.5 times bigger than this. So the maxima will now go to 2.5. On the negative side also it will be at -2.5, and the minimum of this amplitude modulated wave, since we have considered its amplitude as 1.5, so its minimum will go to -0.5 and similarly to +0.5. So if I have to draw the amplitude modulating wave, I will go like this. Let me first draw this dotted line. This will tell us where exactly we have to stop. So this will go like this, it will come here and then it will go again. So that is the cyclic signal of our original signal, which is the modulating signal. Similarly from the negative side also it will go like this and it will attain its minima here, and this has to join here. So let me redraw it. So it will be like this. Like this, and the amplitude modulated wave will now behave like this. So amplitudes are added, so it will start from here, it will come here, then like this, this, and inside this small band also there will be vibrations. The frequency of amplitude modulated wave is not going to change, only its amplitude will change as its name suggests, like this. Now if you pay close attention, the shape of amplitude modulated wave is now very different from the shape of our original message signal. The modulating wave, the shape has changed quite a lot. Let us have a look on the graph. So this section is unwanted. Similarly, this section is unwanted, because at the receiver end, although this signal was not present in the original message, it has now appeared in the amplitude modulated wave, and this will distort our signal. So for an efficient communication using amplitude modulation, the value of mu should not be larger than 1. We have just seen that what happens when mu is larger than 1, an unwanted signal is added to amplitude to the original modulating wave. So that's the reason why we don't want the amplitude of our carrier signal to be smaller than the amplitude of our original message signal. To complete this discussion, let us see what happens when mu is equal to 1. Once again we draw on the y axis the electric field, x axis as time, and 1 is the amplitude of carrier wave. On the negative side it is -1, and 1 is also the amplitude of our modulating wave. So the maximum will be +2 here and -2 here, and our modulating wave will now have maxima at 2 and minima as 0. So it will behave like this, and from the negative side it will come here, and wave will be very nicely represented as such. And the amplitude modulated wave will now be represented by this blue curve, and we see that at minimum it is 0, not exactly minimum at 0, but there is no unwanted signal. And if we see the envelope of amplitude modulated wave, the envelope of amplitude modulated wave now represents the original modulating wave very nicely. There is no information that is lost if mu is equal to 1. So, the maximum value of amplitude modulation index can be equal to 1 for an efficient amplitude modulated transfer. Now, let us try to see, once we have fully understood what is an amplitude modulated wave and what can be the ratio of the amplitudes of the carrier wave and the modulating wave. Now, let us try to see how this amplitude modulated wave is excited. Let us go to the next page, and now we are going to see the generation of amplitude modulated wave. To generate amplitude modulated wave, we first of all add the two waves. One is our message wave, let us represent that as MT, that was our original modulating wave, the voice signal or the video signal that has been converted into corresponding electric variation. So, we add this modulating signal to a carrier signal. So, I will write this as MCT, or if we go back to our original representation, this indeed is equal to E modulating wave and this is E carrier wave. So, this first of all goes to an adder which adds the two waves. The next block is a square law device. So, once these two MC and MT are added, what we get is, let us represent that as XT. So, XT is basically MCT and MT, and the second block is square law device. What this square law device does is, it produces, it takes XT as input, produces YT as output such that YT is equal to some constant times XT plus another constant times XT squared. The square law device is typically a non-linear device. What does a non-linear device mean? Is a device that produces a signal which is not linearly related with the original signal. Linear relation is like, let us say y is equal to mx, that is a linear relation. This y is a function of x, and non-linear will be represented at mx plus, let us say, n x squared. So, there is a higher power on x also. So, this is a non-linear equation. So, the power can be anything except 1, that will represent a non-linear equation. Now, the third block is a band pass filter. We will see why this is needed. This is also an important block. This is band pass filter. Now, let us see what happens when we are sending our input, that is the message signal as well as the carrier signal, to this device. So, what happens at the first block, that is adder. So, after adder, so let us write after adder, the signal that we get is xt, which is equal to mt plus mct. That was our first block. Now, second block is the square law device. So, after square law device, the output will be yt being equal to cxt plus bxt, let me rewrite it, bxt plus c xt squared. Now, going back to our original equation, if we are representing mt, which indeed is equal to E mo, let me write d also, otherwise we will confuse with m naught. So, this was represented as E m naught sine of omega mt. E m naught is the amplitude, omega m is the frequency, angular frequency, and E c t, which is now equal to mct, and this is equal to E m, not m, it is the carrier wave. So, it will be E c naught sine of omega ct. So, if we use these two representations for the x for the mt and mct, after adder what we will get is, we will get xt as being equal to E m naught sine of omega mt plus E c naught sine of omega ct. Similarly, after square law device, the signal that we will get will be given by yt, and that is equal to bxt plus cxt squared. So, this will be equal to b E m naught sine of omega mt plus E c naught sine of omega ct plus c E m naught sine of omega mt plus E c naught sine of omega ct squared. Now, let us expand this. What we will get, yt will become equal to b E m naught sine omega mt plus b E c naught sine omega ct plus c E m naught squared sine squared omega mt plus E c naught squared sine square omega ct plus 2 E m naught E c naught sine omega mt and multiplied with sine omega ct. Now, let us use the following substitution. First one is that sine square omega t can be written as 1 minus cos 2 omega t divided by 2, and second substitution that we are going to use is sine x sine y is equal to half of cos x plus y, this is a negative sign, and plus cos of x minus y. So, we are going to use these two substitutions to simplify yt. Let us see what we get. So, as the expression of yt, we will get b E m naught sine of omega mt plus b E c naught sine of omega ct plus c and E m naught squared 1 minus cos of 2 omega mt divided by 2 plus E c naught squared 1 minus cos of 2 omega ct divided by 2 plus E m naught E c naught cos of omega c minus omega m t and minus Em naught Ec naught cos of omega c plus omega m t. And this becomes equal to b Em naught sin omega m t plus b Ec naught sin omega c t minus c Em naught square divided by 2 cos of 2 omega m t minus c of Ec naught squared divided by 2 cos of 2 omega c t plus Em naught Ec naught cos of omega c minus omega m t, and of course, this has to be multiplied with c minus c times Em naught Ec naught cos of omega c plus omega m t, and the remaining part will be plus c Em naught squared plus Ec naught squared divided by 2. So, if we pay close attention to this equation, we see that this equation contains a lot of frequencies. This equation contains at least 6 different frequencies. Let us see what they are. So, the first frequency is omega m, that is our frequency number 1. Frequency number 2 is omega c. Frequency number 3 is 2 omega m, that is our third frequency. Frequency number 4 is 2 omega c, that is our frequency number 4. Frequency number 5 is omega c minus omega m, and frequency number 6 is omega c plus omega m. And this is DC part. This is DC part. So, what we saw is, let us write it, we saw that after passing through the square law device, the resultant wave has 6 frequencies, and they are number 1 omega m, number 2 omega c, number 3 2 omega m, number 4 2 omega c, number 5 omega m plus omega c, and number 6 omega c minus omega m. Now, if you remember correctly, the 3 frequencies that should be present in an amplitude modulated wave are omega c, that is the carrier frequency, and only 2 side lobes, one at omega c plus omega m and the second one as omega c minus omega m, whereas we are getting 6 different frequencies plus some DC part as well, which does not depend upon any frequency. So, to get rid of these unwanted frequencies, we need to have a band pass filter that is centered at omega c and which can pass the frequencies starting from omega c minus omega m till omega c plus omega m. So, what we do is, after this square law device, we pass it through a band pass filter. So, band pass filter allows only omega c plus omega m and omega c minus omega m to pass and blocks all other frequencies including the DC part. So, at the output now we will have all these 3 frequencies that are needed. So, after this, at output of band pass filter, what we get is the equation will become E m, let us go back and have a look. So, this will be B E C naught. So, at the output we will have B E C naught sine of omega c t plus we will have C E m naught E c naught into cos of omega c minus omega m into t. Let me rewrite it nicely. So, the second term will be plus C E m naught E c naught cos of omega c minus omega m t, and the third term will be C E m naught E c naught cos of omega c plus omega m t, as was needed for amplitude modulated wave. So, this will be our y t. Now, typically the power of this amplitude modulated wave that we have just generated after passing the modulating wave and the carrier wave through an adder first and then to a square law device, the overall power of the wave that has been produced after the band pass filter is very small. So, generally after passing the waves through a band pass filter, we use a power amplifier also. It is to increase the power of the amplitude modulated wave so that it can be now transmitted, and the requirement of any repeater or any amplifier is reduced. So, the third element, after passing through an adder and then to a square law device, and then to a band pass filter, generally it is sent to a power amplifier. So, this was our message signal, this was our carrier, these two produced x t, which was simply a summation of message signal and the carrier wave. Square law device produced y t, band pass filter then produced amplitude modulated wave. This was amplitude modulated wave, and from power amplifier now it is sent to an antenna. This is our antenna. So, once we have understood how this amplitude modulation works, let us now try to have a quick look on our second kind of modulation, that is frequency modulation. So, the second topic that we are going to study now is what is a frequency modulation. So, in frequency modulation, the frequency of the carrier wave is changed in accordance with the modulating or our message wave. So, if we represent the electric field of carrier once again as E c is equal to E c naught sine of omega ct, this is our carrier wave, and the electric field of message wave as E m is equal to, or let us say modulating. So, MOD is equal to E m naught sine of omega m t. The wave that is produced, the frequency modulated wave, will have its equation given by E f m. Its amplitude will not change, but its phase will change. It will become omega c t plus theta. Let me rewrite it. It will be sine of omega c t plus some theta. Now, this has been changed in accordance with message wave. So, in frequency modulated wave, we see that the amplitude of the frequency modulated wave does not change, but its frequency does change as per the modulating wave or our message wave. So, the overall representation of frequency modulated wave will be E c naught sine of omega c t plus theta. Now, if omega I is the instantaneous frequency of the frequency modulated wave, then it can be written as omega I is equal to omega c plus there is delta omega sine of omega m t, where omega c is carrier frequency, delta omega is carrier detuning, and omega m is modulating frequency. In order to get the complete equation of frequency modulated wave, what we have to do is we have to represent the overall phase of the frequency modulated wave in terms of the frequency of carrier wave as well as the frequency and amplitude of modulating or our message wave. Let us try to see how that is done. We know that angular frequency omega is given as 2 pi times the frequency, or that is equal to rate of change of the angle. So, we can write omega as 2 pi nu, and that itself is equal to d theta over dt. So, from this equation we can rewrite d theta as omega dt, or if we want to get theta, then we have to integrate this, that will be equal to integration of omega dt, that will give us the phase. So, we can write theta as equal to omega I dt if we want to calculate the overall phase of our frequency modulated wave, and this overall phase of the frequency modulated wave will now be equal to omega c plus delta omega sine of omega c t, this is omega m t, because the frequency of modulating wave is omega m. So, if I integrate, I will get omega c t minus delta omega divided by omega m sine of, no, it becomes cosine of omega m t. So, this will be theta. So, the equation of frequency modulated wave becomes as EFM, that will be equal to EC naught, the amplitude of the carrier wave does not change, sine of omega Ct minus delta omega over omega m cos of omega m t. So, this is the mathematical representation of frequency modulated wave. We define frequency modulation index just like we had defined the amplitude modulation index as delta omega over omega m, or this can be represented as delta f over fm. So, that is the mathematical representation of a frequency modulated wave. In the next lecture, we will start discussing about the receiver part of this electronic communication system. We will study how the amplitude modulated wave that was transmitted through an antenna is received and how the original message signal is retrieved after the signal amplitude modulated signal has been received at the receiver end. Thank you very much.